what I want to do here is that I want to kind of step aside of this. And I think what I'm going to do here is I'm going to take this and I'm going to slide this down. And I'm going to do an aside here. I'm going to do an aside on Newton's second law for circular motion. So let's look at this thing here. So what we find here is that for circular motion, the acceleration pointed inwards is called the centripetal acceleration. In other words, if I have something moving in a circle, and let's say that I have an object like this, and this object is moving in this direction, and the way we typically look at this thing, we imagine here that this is some string that's tethering this red ball here. What causes this ball to move in a circle here is the string. And so what you're seeing here is that in this case here, the net force is pointed down. And if it's pointed down, then that means that there must be acceleration in this direction. So the cause of centripetal acceleration is the net force. And the sad thing is that this word centripetal has been misused for many, many, many years. And it will be continued to be misused. It's the net force that's causing that ball to move in a circle. A fancy name for the net force when you have circular motion is the centripetal force. So when somebody says the centripetal force, they really should be talking about what? They should be saying the net force. But we say centripetal force because we have circular motion. There are many people that say, oh, there's a centripetal force acting on that object, and they treat that as a separate force. That's a meaningless statement. Centripetal force means net force. There is no individual force called the net force. The net force is the sum of all forces acting on an object. That is a meaningless statement. So in this case, when I write the net force, it would be the tension. And this tension here is equal to mass times acceleration. Okay? So the tension is equal to the mass times the acceleration, but because this is in circular motion, we typically add a little c for the centripetal acceleration, where the centripetal acceleration, we can derive this thing. It's not a hard thing to derive, is v squared divided by r. So v is the velocity, r is the radius of the circle. Okay? That's what centripetal acceleration is. And so, there's there's a lot of situations that we could think about it. And the one thing that we're going to do here today is that we're going to primarily look at a circular motion because we're going to need that for this example. And so check this out. Now imagine that we take a ball and we are going to swing this ball in a vertical circle. So suppose a ball on a string is moving in a vertical circle. Okay. So what I want to do here is that I want to go in and I want to look at this thing using Newton's law. So you could imagine that this is a circle here, right? Here's my path. And of course, here's the center of the circle. And I want to look at this ball at multiple locations. So I want to look at the ball right here, right here, right here, and we're right here. So we'll call this point 1, 2, 3, and 4. So my question is, what is the net force? Remember, I can also call this the centripetal force. At points 1, 2, 3, 4. Okay, so let's go do that. Let's do the free body diagram. So if I look at 1, let's look at a string here. So for the sake of simplicity here, I'm going to do a blue string. So as the ball is moving at 1, right? So that means that the ball's going like this. And in each of these situations, the velocity is pointed like that. So if I look at point 1, let's draw the free body diagram. So if I draw the free body diagram, you could see that here's my dot. You're seeing here that there's a blue tension. And because this is in a vertical circle, this is what? mg. So what's the net force? Well, look where the force has to be here. So in this case, maybe I should draw this to scale. My mg is going to be small right there. So what you're seeing here is what? The net force is in that direction. Why? Because if I call that plus and minus, you could see here that this guy's going to be tension minus mg. And the tension must be bigger than mg because it's being accelerated towards the center. Why? Because the centripetal acceleration is always there. So the question, what is the centripetal acceleration at point 1? Well, it's T minus mg. That's the net force on there. Therefore, that's the centripetal force here. And if I go to point 2, and if I look at my ball right here, you could see here is that mg is going down, but now the tension force is going to the left. So the question is, which direction is the net force now? Actually, it's over here. The direction of the net force is in this direction here. However, what is the centripetal force? What is the force that is pointing towards the center of the circle? So in this case, here's where it makes sense. So here, we could write this as Fc at point 1, but here we could see that the force in the x direction, which I'll make that to be positive, this guy is the centripetal force. Why? Because the acceleration is in this direction right there, because it always points towards the center of the circle. And so what's the force? What's the centripetal force that's applying the centripetal acceleration in this case? It's going to be the tension. And then if I go to point 3, look what I'm seeing here. At point 3, you're seeing that this time there are two forces acting. In fact, I'm going to put it up here. And what you're seeing here is that there's mg and there's tension. So these guys are both pointed in the direction towards the center of the circle. So then I ask, what's the net force? Or I could say, what is the centripetal force? That's the component that points towards the center of the circle. And in this case, it's going to be T plus mg. That's what the centripetal force is. And when I get to point 4, you can see that point 4 is going to be very similar to point 2, but this time it got turned around. So you're seeing that this is the direction of the tension. I'm getting mg coming down. So there is a force, a net force that's, down in this direction right here. Right? That's going to be the net force. But the question is, what is causing the centripetal acceleration? And again, the centripetal acceleration points towards the center. So we then say that the force in the x direction, which is the same as the centripetal force, is once again the tension. So the language of the centripetal force and the net force is of course the same. There is no such thing as a centripetal force per se, because there is no individual force called the net force. The net force is the sum of the forces in the direction of the acceleration. The centripetal force is the net force in the direction of the acceleration. They're one and the same. But now I want to look at the physics of this thing here. And the physics of this thing, which is super important to hear, is that I want you to think about the ball moving up to the top. So now I want to look at when the ball moves the fastest and the slowest. So if I look at my equations, the only 2 points that I really have to pay attention to is point 1 and point 3. So if I look at point 1, N2L tells us here that the net force, which is the same as the centripetal force, is then going to be T minus mg, and this is going to be ma centripetal. Now note, I can write ma centripetal as mv squared over r. Okay, so when I look at the speed in this case here, what this tells us here is that the tension is highest at the bottom of the circle. And that tells us here that the tension then is then going to be what? mg plus mv squared over r. But wait a minute, if I have the highest tension there, that's the force that's in the direction of the acceleration here. So therefore, this tells us that this has to have the highest speed. And physically, that makes sense. That if you're coming down, that's where you're going to be moving the fastest, right there. I want to do the exact same thing with point number 3 here. And when you look at N2L, the net force at point 3, which is also the centripetal force at 3, is then going to be tension plus mg. And of course, this will be mv squared over r. So now look at what the tension is. If I look at this scenario here, we see that the tension is smallest at the top. And when I write the tension equation, what am I actually calculating? I'm seeing that T will then be, look at this, mv squared over r minus mg. And you know what? I should have probably erased it and written it in this form. You can see here that the weight is increasing the tension. Here it's reducing it. So this is the critical thing that I want to focus on right here. So in order for a ball to make it to the top of the loop, there must be tension in the string. That's the only way. And what you're seeing here is that there's a critical point. And this critical point here is that T critical is this guy is actually equal to 0. And what it's telling us here is that this is the critical point. That means that mv squared, and this is a critical speed here, divided by r minus mg. And this is the minimum speed required to complete a full loop. And when you calculate this number, you're seeing that V critical squared is then going to be equal to, look at the masses, what are they doing? They're canceling out. So this critical value is actually equal to G times R. So if you want something to go around, its velocity squared must be equal to GR. So now that's the minimum speed. So what you find here is that then I then put I can have a speed faster than that, but I have to have this. So this is the important point for our next example here. Okay, that is the important point. And so now that I got the minimum speed required to make a full loop, then I could now go and look at this example. And that's what I want to do right now. So what I want to do here is that I want to go in and I want to start looking at what we've done in the past here. Okay. So what we want to do here is that I want to come in and I want to try to get a sense of what this example is telling me. Here, hold on a quick second. Let me set up here. Okay, so here I go. So what I want to do here is that I want to come in and let's see. How do I want to start this? I want to start this nice and clean. So Well, let's go through the problem, and then if I have to modify, I'll modify as I go along. I'm just trying to prepare you the best before we get there. So let's look at this first question here. It says, so I have a pendulum. It has a length of 1.25 meters. Its bob, which is the heavy mass, which effectively has all the mass when the cord here. So by the way, we should talk about this. I don't know if we've talked about this. Is there such thing as a massless string? And the answer is, of course, there's no such thing as a massless string. You can't go to the store and buy a massless string. However, there's a very good approximation of a massless string. And the way we do this here is that if the mass of the pendulum bob is much, much greater than the mass of the cord or the string, then this is a massless string. That means we can ignore that, and to many sig figs, you could literally replace the mass of the string equal to 0. So what we have here is that we have a bob that has a very large mass compared to the string. We see that the length of the bob is 1.25. That is the string that's attached to the bob. So they're asking, what is the speed when it's at its lowest position if the initial speed is 8 meters per second? Okay, so here we go. So we want to
Hey,
look at...
Carlos, quick question. If the mass of the bob is so much greater than the mass of the string, then how does the string support the mass of the bob without snapping?
Well, that's a good question.
Huh.
I guess we have to have some realistic thing here. Let's
Yeah.
say that I have a 10-pound bob. And if I look at some of the fishing string, right, very light fishing string can handle more than 10 pounds.
Right. Oh, okay.
So if I look at the mass of the fishing string, I would say that a 10-pound bob is much, much larger than the mass of the fishing string.
Oh, okay.
So then I'm going to say, yeah, that's a massless thing.
Oh, okay. I get it now. Thank you.
Okay, no problem. And so what we want to do here is that we want to know what the speed is at its lowest position, right? So the question is, what is the speed at its lowest position? So the question is, what's our system? Right, so let's look at our system. Well, for starters here, we have a connection where the bob is going to be connected, right? And then we have the bob. So let's say that in this case here, I'm feeling a little bit purple right now, so I'm going to use a purple bob here. And we know that the bob is then going to be moving what? In this direction right in here. Because we're going to release it. And they tell us that that's what the initial speed direction is going to be. So what are the forces on this thing? Well, we should include the force of gravity. Because this bob can move because we're talking about what? We're talking about Earth. So we know that there's a force of gravity acting on this thing. Are there any other forces? And the answer is yes, there's tension. So let's look at tension now. So when I look at my system, right, here's my system. So we know that the force of gravity is conservative. Okay, so F of G is conservative. So that implies we can use the gravitational potential. question is, what about the tension? The tension is in the system, right? We have to deal with the tension. But note here, note the displacement is always perpendicular to the tension, right? So in other words, I could say, yep, here's my tension. And then I look at my displacement and I see that my displacement looks like this. There's always a 90-degree angle between the two. Wait a minute. That tells us that the work of the tension is zero. And if the work is the tension, then that means it does not change the energy of the system. Because remember, the work done by the tension here, since it's perpendicular is zero, that means it will not change the energy of the system. So we're good. So we can have the tension. Okay, so let's look at that. So note that the tension's okay in the system because it doesn't change the kinetic energy or the potential energy of the system. So here we go. So now I want to look at the bottom. So let's set up a picture here. So the picture that I'm setting up here is that it goes something like this here. So now let's sketch the situation. So if I sketch the situation, here's what I'm seeing here. I'm seeing here, right? I'm seeing where the bob is attached. So then I'm going to come over here. It's going to go right here. And then here's my bob. And what I'm going to see here is that my bob is then going to come all the way down. And we're going to say that this is its lowest point right in here. And what you're seeing here is that I know that what happens here. I did not see what happens in A. What is the speed of the bob when it's at its lowest point? If the initial speed is 8 meters a second. So what we do know here is that right in here, we know that it's initially pushed so that it's moving 8 meters per second. God, am I reading this right? I want to make sure I get this right. Right? What is the speed of the bob when it is at its lowest point if its initial speed is 8 meters a second? Okay. Okay, so that looks right to me. And the other thing that they're telling us here is that this angle right here is 40 degrees. Okay. And then when it gets to its lowest point, we want to ask the question, what is the speed here? So what I'm going to do here is that if I call that initial, I'm going to call this guy V1. What is the speed down here at the bottom? Now note, I could set my reference potential to be anywhere I want, and it seems like a good place to choose here is to choose y1 here equal to 0. So then my height from here to here, y initial, is something that we start off with. So if I know the length of the string, I know the angle, I could calculate y initial, and I know that at the bottom, I know what its final height is, and I don't know what the speed is. So what I'm going to say here is that this energy state, I'm going to call my number one energy state, and this is known. Why? I know the initial speed, and I know the initial height, which I can calculate, and then my point, oh, I said that 0.1, I should say 0.0, sorry about that. My 0.1 should then be my unknown energy, because I don't know what that final speed is right there. So here I go. I want to go calculate this thing. So if I go and I calculate this thing, what do I know about this thing? Well, the first thing that I'm going to see here is that if I have this thing, what's my picture-wise? Picture-wise, I'm seeing that this bulb starts off with this amount of potential energy, right? It has that amount of potential energy. Now it has kinetic energy. It has some initial kinetic energy here. And this is what I'm going to call the kinetic energy at 0. And then afterwards, since there's no external forces doing work, I know that the final kinetic energy of the system should be like this. And as expected, we expected a higher speed at the bottom. So we know what to do here. We know how to come in and write this thing, because now conservation of energy just says, hey, my known energy state versus my unknown energy state then tells me that I got to write K initial plus mg y naught equals, oops, I should write UGO equals K1. So if I write everything out, I'm going to get 1/2 V initial squared plus mg y naught, and this will be 1/2 mv1 squared. So this is what we're solving for. We want to solve that. We know this because they tell us that that's 8. And so this guy we have to calculate. And so this is one of the trickier height calculations. So let's go calculate what that is here. So now what we want to do here is that we want to calculate y initial. And so the way I'm going to do this here is that I'm going to steal this image right here and then erase a couple of things. Okay, so here we go. So I have this thing here, and then I'm going to take some of these guys out of here because I need that height here. Okay, so now what I want to go in and do here is that I want to come in and I want to calculate what this height y initial is here. So the thing that you really want to pay attention to is this triangle right here. So when you're looking at this triangle, it's this guy that you want to focus on. And the reason why this is here is that what we know here is that the length of this string here is 1.25 meters. And even though they don't look the same, this length right here is also L. And of course, this must be the case here because I just haven't drawn this to scale. And what you're going to see here is that note that there are two distances that we want to pay attention to. Well, we know the height of the bob. We already defined that as y initial. And what I'm going to do here is that I'm going to define a second distance from here to here, which I'm going to call x. And what we find here, we see that L must equal x plus y naught. So if I can calculate, so the way to get y initial here, so then this tells us here is that y initial must be L minus x. So this is the guy that we got to calculate. And what you want to do here is that look at that green triangle. So we calculate this from green triangle. And when you look at that thing, what you're seeing here is that note that the angle is the adjacent angle. So therefore, I have to use the cosine because it's the adjacent angle. So if you look at this thing here, what this tells us here is that if I look at the adjacent angle, this tells us here that x over L must be cosine of 40. Or x is going to be L cosine of 40. So I now know what x is here. So then if I now substitute back into y initial, I'm going to get L minus L cosine of 40, which then it's common not to write it this way, but the way we'll write it here is we'll write 1 minus cosine of 40. And this is what y initial is. So now I have my expression right here. I now know what the height is here. So now I'm going to go apply conservation of energy. If I go apply conservation of energy, what am I seeing here? Well, conservation of energy says this. It says, so from energy, we already agreed that we had 1/2 mv initial squared plus mgy initial equals to 1/2 mv1 squared. So then I'm going to solve for v1, and v1 should then be, check this out, I have masses on both sides, so I could cancel that out. So if I look at this thing, and if I do some algebra, you're going to get 1/2 v initial squared plus g y naught divided by 1/2. Now if I plug in this guy here, you're going to get v initial squared plus gl of 1 minus cosine 40 square root. And when I'm going to go calculate this guy here, ooh, I did not calculate this thing correctly. So I'm going to have to punch this into my calculator here because I don't have the right number. Because this should be 8 squared plus g of 1.25 meters times 1 minus cosine of 40. So if somebody has a calculator, punch this in with me because I'm notoriously bad at putting things into calculators. So let's see if I can get this. Oh, okay. I have an error someplace.
Carlos, shouldn't there be a 1/2 in front of the V naught and on the denominator?
Yeah, I actually brought the 2 up, but the 2 should be right here. Thank you.
Okay.
Yeah, it should be right there. I can't in great fashion here. I got an error on my calculator, so let me try one more time. Oh, damn, it keeps telling me I have a missing parentheses. So it looks to me that I get 8.28 meters per second. Now, if somebody could verify that, that would be wonderful. But I'm not holding my breath on that that's the right number. So let's say that that's what the speed is. So I've now done part A. And the whole point of part A is really to get this height calculation, which I think is tricky. Okay, now let's go read the next piece of it. I'm going to copy this and bring it down with me. Okay, here I go. So when I'm looking at this, I'm now looking at B here. And it says here, what is the least value of V initial if the pendulum is to swing down and then up to a horizontal position? Okay, let's go look at that. So my picture looks like what? Well, this time we don't know what the initial speed is. So what I imagine in this scenario here is that I have this thing that I'm looking at. this is where it starts at. Excuse me, this is where the string is pivoted upon. And so I'm going to have something that goes like this. And then here's my bob. And what I want to do here is that I want to take this thing and I'm going to push it here. Now I used V initial and then I use V1. So now I'm going to call this V2. I want to know what speed do I have to push this at so that it comes all the way down and then it comes all the way up to this position right in here. So what speed do I have to give it till it reaches that one point right there? Well, let's see if we can get an image of what we expect here. Well, I think it's useful again to still think about this as being our ground level, right? Here's our ground level. So I know what this height is right here, right? This is going to be y3, no, y2, sorry about that, y2, and we already calculated that height. So if I'm starting from the same height, this should be 1 minus cosine of 40 degrees, like this. So we know how high the ball starts, and then the ball is going to come all the way up to here, and look at what this height is. That height should be the length of the string. Okay, and this is assuming that this guy gets to this height right here. So what we're seeing here is that I know that this guy is still 40 degrees like we talked about before. So if I think about this thing picture-wise, what does conservation of energy tell me here? Well, I know for a fact that this guy has to be what? It has to be my gravitational potential at this point. And then I have to push it with some initial speed in such a way that it has to go all the way up to the top here. So that this is my kinetic energy 2. So when I get all the way to the right over here, or excuse me, the left, then all of this height must be converted into gravitational potential. So if I call that 2, I should then call this 3. That's my energy bar diagram right there. So now I know how to write conservation of energy because I know that this is my energy state number 2. So this guy 2 is my unknown. And then energy state number 3, because I know if it gets up to that point, we assume that at this point, V3, if that's where it stops, it has to be at rest. So this guy here must be my known energy. So now I can compare those two together. So let's go write this out. So if I go write this out, what am I going to get here? So according to conservation of energy, then I could then come in here. So from energy, I can then say that the energy at 2, which is unknown, equals my energy at 3, which is known. And that tells me then I could then write what? According to this, it's got to be K2 plus UG2, and that has to equal UG3. So then I start writing out my equations here, and I could see here that this is going to be 1/2 mv2 squared plus 1/2, oops, not 1/2, it's going to be mgy2, and this will equal mgy3. So again, this is what we want to solve for. This guy is known. We've already calculated from the previous problem, so we know this here. And this guy right here, we know also because that's the height of from the bottom up to the top here. We know this here. This is the length L. So now I'm going to go ahead and solve for this thing here. So if I solve for this guy, what do I get? Okay, so solving for V2, then I'm going to get, so this, since this is very similar to before here, let's look at this thing here. So I got to subtract, so I'm going to get, so once again, you could see here that the m's are canceling out, okay? The m's are canceling out. So what I'm going to see here is that I'm going to get g of y3 minus y2, and then look at the 1/2. I'm going to multiply that by the 1/2 on both sides, and I get, or by 2 by both sides, and then I get the square root. But let's start putting in these values here. I know y3 must be the length of the string. I know that y2 must be L minus cosine of 40. So if I plug these guys in, I then should have what? I'm going to get 2g, and then I'm going to get L minus L plus L cosine of 40. And you could see that these guys are going to cancel out. So now I finally get a relationship that reads 2GL cosine of 40. And if I compute this thing, remember that we know the length here is 1.25 meters. So if I compute this, I'm going to get a value of 4.33 meters per second, which will then be the speed of V2. Okay, so now when I look at this thing, I know that this must be the case. I know what V2 is right there. So now we come to the tricky part. So let's go look at the tricky part. The tricky part is part C. So what happens in part C here is that it's going to go to a vertical position. If it goes to a vertical position, now we have to worry about this thing. And the thing that we got to worry about is that in this situation here, what we're doing here is that we know that the speed can't be 0 at the very top. Okay, so let's go look at to see here now. So what we're seeing here is that, let's look at this from physics-wise, and then let's try to keep this. So now we've dealt with energy states 1, 2, and 3. So this one, I'm going to call, what did I do? I called this 2, and I called this 3. So I'm going to go with 4 and 5. So what we're doing here is that this is the picture that we're trying to get here. I know that I'm going to swing this guy all the way up to the top. So let's say that this is this here, and that means here, actually, I think I'm going to move it over a little bit. And so what we're seeing here is that this guy here, let's say that this is the pivot right here. Here's the string right here. And this guy's going to, let's say it's going to do this type of thing. So the ball's going to come all the way around. And it's going to start from this location right here. So what do we know about this location? Well, we know that this guy here has an angle of 40 degrees. And what we're going to do here is that we're going to come in here and we're going to add some speed. We're going to call that V4. We want to know how fast do we have to push this ball in order that it gets all the way up to this point here. So clearly you could see that I'm already defining this as my unknown state. And this number 5 here is my known energy. So what do I know? Well, I think it's clear that the height of this ball is 2L, all the way from the bottom, where we now call y at this point equal to 0. And so what do I know here? Well, from our previous discussion, the question is this. Can the ball have 0 speed at 0.5? The answer is a big no. The ball will never make it. And the way we do that here is that to see this is that we apply Newton's second law for circular motion. And what we said before here is that if you're looking at the top, look as the ball is moving up to the top. As ball moves up towards the top, you're seeing the following thing. So what you're seeing here is that if I'm looking at the string and the ball's moving in that direction, what you're finding here is that you got mg going down, you got tension coming down, and we have our acceleration going like this here. And what we saw here is that when we applied the net force, which we call the centripetal force in this case, we saw that this was tension plus mg had to be mv squared over r, where v squared over r is the acceleration. So the question is that in order for the ball to move around the loop, there must be a minimum tension. So for the ball to move around in a loop, there must be at least a minimal tension. And so what we said here is that we calculate this critical tension. We calculate this critical speed here. And what we found here is that there's this critical value where we say that T critical is equal to 0, then tells us that mv squared critical over r minus mg. In other words, it tells us that the critical speed must be gr. That's our critical speed. If you don't have that minimum speed, then you won't make it around the loop. So in other words, this guy has to be greater than or equal to that. Okay, so that's the condition. So this is the condition for a ball to make it to the top. That is, the ball must be moving with a minimum speed of v squared critical equal to gr. You have to have that. So let's go do that. So then if I look at my bar diagram for the situation, I'm just going to keep doing the same thing that we did before. So then I'm going to bring this down here so that I can draw a bar diagram just to make sure that we're clear. And let's draw this here. And so what I'm going to do here is I'm going to put this right here. And I'm going to take this stuff off because we already know what that means here. So here I go. So what do I have? Well, I know that this is my gravitational potential here at 0.4. And to get up all the way up to the top, I have this amount of gravitational potential. So we have our gravitational potentials here, right? So I have my gravitational potential. So now let's look at my kinetic energy. Well, I know that when it gets to the very, very top, we know that it has to have a minimal kinetic energy. It cannot be zero. So I'm going to say that this is my minimal kinetic energy at 0.5. Therefore, in order to get up to this height, I'm going to have to swing the hell out of this guy here. This must be my initial kinetic energy. And so we expect it to be huge. And so you could see that this is my equation now. So here I go. So if that's the case here, I have a condition. I have a condition that at K5, right? Let me write this a little bit more in detail just to be clear. At kinetic energy 5, there's a condition. The condition is that V5 squared must be G times R. That's the condition. So if that's the condition, then here I go. So what we're seeing here is that we're seeing a couple of things here. Note that if this is the length of the string here, and then from here to here is the length of the string, we could see that the gravitational potential at 5 has twice the height. We know the height here already. We've already calculated this. So this is L4, which we already wrote once as L times the quantity 1 minus cosine of 40. So let's keep doing this. So now here I go. Here's E5, which is my unknown. And this is, nope, that's E4. And this is E5, which is my known. So then I'm just going to write my equation. Here I go. I got UG4 plus K4 equals UG5 plus K5, with the condition that V5 squared is going to be G times L, since R is equal to L. That's the radius of the circle. So then I keep writing my terms here. So here I go. mg y4 plus 1/2 mv4 squared. And then I'm going to get mg5 plus 1/2 mv5 squared. So what do I know? Well, I know this guy. We know that that guy, of course, we know that that's L times the quantity 1. Here's my unknown. This is what we're going to solve for. This guy we know. This guy has to be 2L. And V5 we know. We know that V5 should be GL. So if I put this all in, look what I'm going to get. I'm going to solve for V4. So look what I'm going to do. I'm going to take my MGY4 to the other side, but first I'm going to cancel all the M's. So now if I do this, I'm going to solve for V4. So if I do that, look how I start off with. I have V4. Look what's on the left here. So I'm going to get G times the quantity Y5, Y4 plus 1/2 times V5 And then look what I'm going to do. I'm going to bring in a 2 here, and I'm going to bring in a 2 here because I'm going to do that. And so then I start to put in my points here. And if I do that, I'm going to get 2G. What's Y5? It's going to be this. And then I get L, 1 minus cosine of 40, plus V5 here. But V5 is the same as GL. So now that we have this, what I'm going to do here is that I can clean this up a little bit. And what you're seeing here is that I want you to pay attention to this term. Look at this 2L here, and then look at this 1L right there. So I'm going to get 2L minus L. I think I have no, I think that's right. So one of these L's cancels. Okay, good. So I'm getting one cancellation. And then what I want you to pay attention to is that there's another L term right here. So I'm going to get L, so I'm going to get 2GL, and then I'm going to get GL. So you're going to see that I'm going to get one term that reads, it should read 3GL. And then I have the second term, GL minus minus. So that gives me a plus. So I get 2GL cosine of 40. So then I'm going to get 2GL cosine of 40. And then that's my square root right there. So the only thing that's different here is that we know that the length is 1.25 meters. And so if I punch that number in, we get a value of 7.45 meters per second. And this guy is the speed at the excuse me, that is not V5, that is V4. That is the speed required of the ball initially to make it all the way to the top like that.